Hello, calculus students. So we're going to be looking at integrals in a new way today. We're going to be using them to find the area between two curves. So I'm going to share my screen and get the presentation going. So hopefully you have your notes in front of you, and you can see that it says that the area between two curves is the area from, or the integral from A to B of the top curve minus the bottom curve. And it's kind of like pretty much what you think common sense would tell you to find the area between. So let's look at this first example. It says set up this graph, sketch the graph, and then set up the definite integral that gives the area between the two curves, f of x equals x plus 1 squared and g of x equals 2x plus 5. So this first one is a parabola that's shifted 1 unit to the left of the origin. And here we have a linear function, slope 2 and y-intercept 5. So I'm going to draw a sketch of this just to get started and have an idea of what this looks like. So I have my y-axis and my x-axis, and we have that the parabola is shifted 1 unit to the left. It would go through here and here. So here's my parabola. And then we have this linear function y-intercept 5. And the slope is up 2/1, or I could go down 2 and 1 to the left. And it's kind of my scale. Whoa, my scale's a little bit off here. All right, so there's our line and our curve. And we are trying to find the area of this shaded region that falls in between. So one thing we're going to need to know is, let me switch colors here a minute, is we're going to need to know where do these intersect, right? What's this point and what's this point? Because that's going to be our limits of integration. So if we look at this, we can see that the line is above the curve. So if I just wanted the area under the line, my integral would go from this point, we'll just call it A, to this point B, and that would get me the area all under the line. If I wanted just the area under, if I did just the parabola, it would get me the area underneath the parabola. But I want the area in between these two. So it's going to be the area under the line minus the area that would fall under the parabola, which will leave us with this shaded region in between. All right, so our first order of business is to find where these points intersect. So I'm going to go ahead and multiply this one out. I have x squared plus 2x plus 1. And I want to know, where does that intersect 2x plus 5? All right, so I'm going to move everything to one side. Oops, I left out my 1. So I have x squared, my 2x's are going to cancel. When I bring 5 over, I have 1 minus 5 would be a -4. And so I can see that x is going to be equal to plus or minus 2. And that's going to be our limits of integration. So our integral is going to go from -2 to 2 of, and again, we look and the line is on top. So I have 2x plus 5 minus x plus 1 squared. And all of that is dx. All right, whenever you're doing these, so that's our basic setup. Whenever you're doing these, you want to try to simplify first if you can before you start to integrate. So I'm going to go ahead, I'm going to rewrite this. This first function is just 2x plus 5. But if you remember, we multiplied this one all out, right? We FOILed here. So I'm subtracting all of those terms. So I'm going to have minus x squared minus 2x minus 1 dx. And once I get it down to the simplified form, I'm going to take my antiderivative and use the fundamental theorem of calculus to find my final answer. So the 2x's are going to cancel. I have a negative x squared. Positive 5 minus 1 is a positive 4. And that's what I'm going to use to find the area between the curves. So the antiderivative of negative x squared is a negative x cubed over 3, or a negative 1/3 x cubed. The antiderivative of 4 would be 4x, and I'm evaluating that from -2 to 2. So first I plug in my 2 everywhere. So 2 cubed is 8. So I have -8/3 plus 4 times 2 is 8. And I subtract what I get when I evaluate at -2. So -2 cubed is -8. That's going to make that a +8/3. And 4 times -2 is -8. All right, so I'll keep simplifying. I have a -8/3 plus a -8/3 would be a -16/3. And then I have 8 minus a -8 would be 8 plus 8 is 16. So I have -16/3 plus 16 times 3, 48/3. Which leaves us with a final answer of 32/3. And that's the area between the two curves. All right, if you look at your notes, it says, in example 1, the graphs of f and g were both above the x-axis. This isn't necessary for finding the area between the curves. What we use is what we call representative rectangles, are often used throughout this unit in various applications of integration. A vertical rectangle of width delta x implies integration with respect to x. A horizontal rectangle of width delta y implies integration with respect to y. So let me show you what I'm talking about here in this example we have. So in this case, we were finding the area between the two curves. So my representative rectangle is just like this piece right here. This would be my representative rectangle. Its height is the difference between the two curves. Its width is delta x, because we're integrating with respect to x. I could also draw a sideways rectangle and integrate with respect to y. And then I'd have delta y as the width of my representative rectangle. And that'll come up more here in some other examples. All right, example 2 says the sine and cosine curves intersect many times, bounding regions of equal areas. Find the area of one of these regions. All right, so I'm going to draw a sketch of our sine and cosine curves. And mostly what we're doing this for is to find our limits of integration. So I'm just going to do the positive side here. Here's my 1 and my -1. And my sine curve is 0 at 0, pi over 2, pi, 3 pi over 2, 2 pi. So 0, this I'll make pi over 2, pi, 3 pi over 2, and 2 pi. So sine goes through here, 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 -1, back to 0. Little review of what a sine graph looks like. I will do cosine in a different color. Cosine curve. Cosine of 0 is 1, then 0, -1, back to 0, and back to +1. So here's cosine. Right, so the area that we are trying to find here is this region in here. So my representative rectangle, if I just draw one here, again, I'm going to be integrating with respect to x. So the width of that representative rectangle is delta x. The height of the rectangle, this height here, is the difference between these two curves. And if we look, we can see that the cosine curve lies above the sine, or excuse me, let me do that again. The sine curve lies above the cosine curve in this region. And I'm going to figure out these limits of integration. And most of you probably know that sine and cosine have the same value at pi over 4. So that first limit of integration is pi over 4. And the next time that they coincide, the next place that sine and cosine are equal to each other would be at 5 pi over 4. right? They're both negative square root of 2 over 2 at 5 pi over 4. So that's my limits of integration. Again, our top curve, remember our blue was the sine curve. So the area between the two is going to be the sine of x minus the cosine of x. And our representative rectangle, we said, had a width of delta x because we're integrating with respect to x. And I'm just going to make that dx. That's what we're familiar with when we integrate. So now I find the antiderivative of this. So the antiderivative of sine would be negative cosine. The antiderivative of negative cosine would be negative sine. And we are evaluating from pi over 4 up to 5 pi. Oop, I wrote that as a 2. That should be a 4. My bad, sorry about that. All right, so first we're going to plug 5 pi over 4. So cosine of 5 pi over 4, right? We're down here when we do cosine of 5 pi over 4. We're down here in quadrant 3. Cosine is negative. But now I have a negative square root of 2 over 2. That's going to make it a positive. So we have a positive square root of 2 over 2. And then here, if I do the sine of 5 pi over 4, that again, that's negative. This is going to make it positive. All right, so that's my first evaluation at the upper limit of integration. Now I'm going to do the lower limits of integration. Cosine of pi over 4 is square root of 2 over 2. That's going to make it negative square root of 2. And sine of pi over 4 is the square root of 2 over 2, and that makes it negative square root of 2 over 2. All right, and I'm going to keep simplifying. Square root of 2 over 2 plus square root of 2 over 2 is the square root of 2. In this parentheses, I'd have negative square root of 2. So a negative square root of 2 would be plus the square root of 2. And so for my final answer, the area between these two curves from pi over 4 all the way up here to 5 pi over 4 is 2 times the square root of 2. All right, it says before the next example in your notes, it says if two curves intersect more than twice, then to find the area, you'll need to find all the points of intersection and check to see which curve is above or below in each interval determined by these points of intersection. So I gave an example here. Let me grab my pen. We're bounded by the graphs of the cube root of x minus 1 and the linear function x minus 1. So I'm going to draw this. All right, so this one we're at 0. Let's see if I can draw this pretty accurately here. Oh, that's beautiful. And then my line, intercepts -1. Oh, that's a line. Try to think of that as being a line. So here's my curve, cube root of x minus 1, shifted 1 to the right, cube root function. And so you can see we have these different regions here. In this first region from 0 to 1, the linear function is on top. In the second region here, this area, the cube root function is on top. So I need to set this up as 2 different intervals. All right, these points of intersection, if you haven't figured them out, it should be 0 here. They intersect, so they intersect here at 0, -1, at 0, at 1, 0. And this one again is 1, 1. If you're not sure, set them equal to each other. Right? I would do, where does the cube root of x minus 1 equal x minus 1? And I would have to cube both sides, or you might even be able to just figure this out on your own. And we get that our x values are x equals 0, x equals 1. And this third point here is the point 2, 1. All right, plug in a 2 here, we get 1. Plug in a 2 here, we get 1. All right, so those are our values, those points of intersection that we're going to use for our limits of integration. All right, so our first region, I am starting at x equals 0, and I'm going to 1, And in this region, the linear function is on top. So I'm going to have x minus 1 minus the cube root function dx plus, and to figure out the next area, it's the region from 1 to 2. And in this region, the cube root function lies on top. So x minus 1 minus x minus 1. Be careful you don't miss your negative signs there. All right, so we're going to start. There's not really a whole lot I can simplify here. So I'm going to go ahead and find the antiderivative. Antiderivative of x is 1/2 x squared. The antiderivative of -1 is negative x. This is the same as x minus 1 to the 1/3 power. So the antiderivative of that would be, I have to add 1, so 1/3 plus 3/3 is 4/3. So I would need 3/4 times x minus 1 to the 4/3. Again, if I check the chain rule here, the derivative of x is just 1, so I don't need to worry about it. If you're not sure if you did the derivative right, do the power rule here. 4/3 times 3/4 is 1. Reduce this power by 1. 4/3 minus 3/3 is 1/3. All right, so there's that one. And I evaluate that one from 0 to 1. This one, I'm going to have, maybe I'll put these in some brackets so we're distinguishing between the two. All right, this one, we just did that antiderivative. So that should be 3/4 times the quantity x minus 1 to the 4/3. All right, I have to be careful with the subtraction so I don't lose my signs there. Antiderivative of x, we said was 1/2 x squared. This is going to make it negative 1/2 x squared. Antiderivative of -1 is negative x. This is going to make it positive x. And this time I'm evaluating from 1 to 2. All right, so first I plug a 1 in everywhere here. So that's going to make this, I'm going to give myself lots of room here. That's going to make this first time through, I'm going to have 1/2 minus 1. This will turn into a 0. When I plug a 1 in here, it's a 0. So I don't need to worry about that. Plus, now I'm going to evaluate everything at 0. Be careful, it doesn't automatically turn to 0, right? This will be a 0, and this will be a 0. But if I do this one, if I plug in 0 here, I have -1 to the 4/3 power, which would be a positive 1. And this is going to make it a -3/4. All right, let me double check my math there a second. 0 minus 1 is -1. Cube root of -1 is -1. -1 to the 4th is 1. This makes it -3/4. All right, plus, now I need to evaluate that other integral. So this time I'm plugging in a 2. 2 minus 1 is 1. 1 to the 4/3 is 1 times 3/4 is 3/4. And notice this time I don't have that nice 0, so it's a little trickier. And then plug in 2 here. 2 squared is 4. That's going to make it -1/2 times 4 is -2. And then there should be a minus here. Right, I have to find the difference between those two. Okay, back to where I was. I plugged in 2 here, that was 3/4. That was -2, plug in 2 here, I have +2. Minus, plug in a 1, that's going to turn to a 0. This, however, will be a -1/2 plus 1. All right. Double check my math here, make sure that's what I got. 1/2 minus 1. 0. And then here we have a -3/4, right? This one we have 3/4 minus 2 plus 2 and -1/2 plus 1. Okay, so let's simplify. So 1/2 minus 1 would be -1/2 And a negative negative 3/4 is plus 3/4. All right. Over here, we've got, these are going to cancel. So we have 3/4. And in the second parentheses, negative 1/2 plus 1 is 1/2. And this is going to make it negative 1/2. Right, so I'm going to simplify all that. Looks like I have a negative 1/2 and a negative 1/2. It'd be negative 1. 3/4 plus 3/4 would be 6/4 or 3/2. And negative 1 plus 3/2 makes our final answer 1/2. All right, so all that work, just find that the area between these two curves, if I add these little areas together, it's equal to 1/2. All right, the next, before we start the next example, it says sometimes the boundaries of a region are more easily described by functions of y rather than functions of x. We can use approximating rectangles that are horizontal rather than vertical, and the resulting basic formula has y instead of x. It's helpful to graph the function to determine whether or not you should integrate in terms of x or y. So we're going to look at one of those examples. It's kind of cool. All right, find the area enclosed by these things. So if I try to solve this for x, or excuse me, solve this for y, I'd bring y over. I'd have y squared is equal to x. I take the square root of both sides and I'd have plus or minus the square root of x. Okay, kind of gross. This one, similarly, if I solve for y, I would bring my x over, divide by 2, and then take the square root. And I kind of have a nasty square root function that I would have to simplify and have a plus or minus. So if I think of these in terms of y instead, or solve for x instead of y, this turns into x equals y squared. And this turns into x equals 3 minus y, 2y squared. So we haven't done a whole lot of work working this way where we have x solved, but it's really kind of nice. So this is a sideways parabola. If you think of, if we had y equals x squared, it would be a parabola that is centered at the origin that goes like this. If we have x equals y squared, it's very similar, except that it's been turned, ooh, not a very good drawing. It's been turned sideways, right? Positive. It's going this way. I don't know if you can see me. All right, this one, same idea. This is a parabola that's upside down, shifted 3 units, and instead of being shifted 3 units up, like we would if it was in terms of y equals, it's shifted 3 units to the right. So what my graph ends up looking like, where these two curves intersect, is we have our first curve, x equals y squared, is a sideways parabola, and 3 minus 2y squared is also sideways. It's shifted 3 units up. The sides are a little bit steeper because we have them with the 2. And so you can see if you were trying to integrate this with respect to x, you would have to find the area between these two and find these limits of integration here. Then you'd need a separate function. So you'd have to do 2 integrals like we had in that last problem, because I'd have to go from 0 to this point of intersection and then here from this one to determine which curve was on top. So if you look, if I use a representative rectangle this time, that is in terms of y. So the width of this representative rectangle that I'm drawing here has a width of delta y, and its height is going to be this curve, the upside down parabola that's 3 units shifted, this top minus this bottom. And it just makes for an easier problem. So now I need to find my limits of integration. I need to know, where do these two curves intersect each other? So I want to know, and they're both solved for x. So the question is, where does y squared equal 3 minus 2y squared? So I'll bring my 2y squared over. That gives me 3y squared equals 3. Dividing by 3, I get y squared equals 1. So y is equal to plus or minus 1. So my integral is from -1 to 1. Remember, it's always top minus bottom. If it's in terms of y, it's going to be right minus left, right? Furthest to the right minus left. So that is this parabola, 3 minus 2y squared, minus the positive parabola, y squared. And instead of writing this as dx or delta x, we're going to write it as dy. Right? And a lot of times on the AP exam, they might throw you one like this where you could do it either way. It's just easier if you rewrite it in terms of x equals instead of y equals. All right, so I'm going to simplify a little bit before I integrate. So I have my 3 and negative 2y squared minus y squared is negative 3y squared dy. I also notice that they have a 3 in common. So remember, we can take constants outside. You cannot take a function outside the integram, but we can take that. So this is 1 minus y squared. And then there's another thing we can do on this one that we also haven't practiced very much. This is symmetric with respect to the x-axis. These are the same distance above and below. So if I didn't want to go from -1 to 1, these are even functions. So I could multiply by 2 and just go from 0 to 1. Do you guys remember that? That was one of our properties of integration. So I could write this as 6 times the integral from 0 to 1. And it's like we're going from here to here and just doubling it. That can certainly work. All right. 1 minus y squared dy. If you didn't see that, it's okay. It would still work, simplifying this one. All right, so I'm going to find the antiderivative. I'm going to leave this 6 for the very end. Antiderivative of 1 is going to be y. Remember, we're working with respect to y here. Antiderivative of y squared is 1/3 y cubed. And our limits of integration, we're going from 0 to 1 instead of -1 to 1 because we doubled it. So we have 6 times. And we first plug in 1. We have 1 minus 1/3. Minus, I plug in a 0 and I get 0. So 1 minus 1/3 is 2/3. And 6 times 2/3. I should get that my answer is 4. All right. Again, if you didn't do that doubling thing, if you had left it like this, it would still work, right? Find your antiderivatives, but you would be using your limits of integration from -1 to 1, but you'll still get 4. All right. All right, it's homework 27 at AP Classroom. If you have any questions, you can email me or ask me in class. Good luck and happy studying.